solver selection in Feko. It's a very commonly asked questions from the Feko community or the Feko user base, and we'll briefly talk about how one can decide which solver is more appropriate for their problem, and we'll also look at the different solver options that we have in Feko. So first, let's understand what computational electromagnetics is. When we talk about solvers, we are essentially talking about computational electromagnetic methods. So these computational electromagnetic methods, these are solutions of electromagnetic equations on a computer. And these equations, they are governed by Maxwell's equations. So ideally, we would know that analytical solutions, they are exact solutions for electromagnetic problems, but they can be available for very simple cases. So for example, on the right, we have, let's say, for an example, we have a cylinder and we have like a spherical object. Now, solving something like this that is easier in structure just by analytical solutions might be easier and faster. But let's say now you're placing that very same cylinder and spherical object onto a more complex structure like a ship structure, for example. Now, trying to solve this problem analytically might not be possible because the complexity of it now increases to a very higher level. So in general, for problems that are more complex, numerical or computational electromagnetic techniques or solvers are required. So essentially, CEM or computational electromagnetics is nothing but a numerical solution of Maxwell's equations, and we derive the solution through approximation of currents and or fields. So when working with computational electromagnetics, we have two main goals. First is to reduce the approximation in order to increase the accuracy. And by doing so, we want to approach or reach the analytical solution result. And the other goal is to make sure that the computational cost, which is the runtime and the memory, is kept to as low as possible. So in FICO, you have several different options when it comes to computational technologies. They can be broadly divided into two categories. So we have full wave methods, and then we have the asymptotic or high frequency methods. Now, these full wave methods are exact solutions of the Maxwell's equations, while these asymptotic or high frequency methods, they are approximation methods. So they provide approximate solutions. So under both these umbrellas, under the full wave methods as well as the asymptotic high frequency methods, we have a couple of different types of solvers. So one thing to keep in mind when working with an electromagnetic software is that no single numerical method can address all applications, and which is why FICO offers multiple solution methods. So when we are selecting a solver for our problem, there are two aspects that one should consider. So first is the electrical size of your structure. Now, electrical size, it refers to the largest dimension of your model. So for example, the length of the ground plane of a patch antenna, as an example, right? So that when it is measured in wavelengths, that can be considered as the electrical size of the solver. And for some applications, the electrical size of the model is the main consideration for the solver type. So let's say if you have very simple uh, structures like antennas that you're trying to design that consist of only metallic elements, you can go with solvers like method of moments or MLFMM. But let's say now that you increase the complexity of the material. So that is the second aspect that one has to keep in mind, which is the complexity of the materials. So as the complexity of the materials increases, you can then switch on from method of moments, which is the default solver in Feko. And method of moments is a full wave solution. So from a full wave solution like method of moments, once the complexity of materials increases, you can then move on to other solver types like finite element method or finite difference time domain method. So similarly, if the electrical size increases, um, instead of using method of moments, you can go for the high frequency approximation methods, um, like physical optics, ray launching geometrical optics, or uniform theory of diffraction. So as an example, if you have a simple structure like an antenna, you can solve it with the default FICO solver. But let's say now the same antenna, if you're placing on a structure like a ship, for example, that increases the electrical size of the model or the structure that you are computationally trying to solve. So in those kind of cases, you can then move on to other solvers like um, MLFMM or physical optics or ray launching geometrical optics. So essentially, the solver selection depends on the complexity of your model in terms of its electrical size as well as the complexity of materials that your structure has. So apart from choosing single solvers, FICO also allows the users to hybridize these solvers. So you can have one full wave solver and one asymptotic solver, both in the same model. One example again could be that let's say you have a monopole antenna, and a monopole antenna you want to place on a structure like a ship. So what you can do is you can solve the monopole antenna with a full wave solver like method of moments, and you can solve the entire ship structure with a with a high frequency approximation solver like physical optics or ray launching geometrical optics. So in this way you can get like best of both worlds. You can get your accurate, you can maintain your accuracy, but then you can also make sure that the runtime and the memory does not exceed beyond a certain point. Now, one more thing to understand is the difference between field methods and source methods when it comes to these full wave solvers. So loosely, these methods can be differentiated into two forms. So your solver can either be a field method. It means that the solution, the base of the solution is electromagnetic fields, or it could be a source method where the base of your solution is currents or charges. So the field method basically uses differential equations, Maxwell's differential equations to solve your problem. And the source method uses Maxwell's integral equations to solve the problems. The main thing to note over here is the discretization. So whenever you solve any problem in FECO or any electromagnetic simulation tool, uh, the software basically divides or discretizes your problem into smaller elements. These elements can either be volumetric or they can be surface elements. So volumetric elements can be elements like tetrahedral meshes or voxel meshes, while the surface elements could be segments or triangles. So based on your problem, you can decide if you wanted to solve it with a field method or a source method. So the field methods that we have in FICO are the finite element method and the finite difference time domain method, while the source methods that we have in FICO are method of moments, which is the default method in FICO, as well as adaptive cross approximation and multi-level fast multipole method. So when working with FICO, as I mentioned, the electrical size of the model does play an important part. Um, so let's say if your electrical size is somewhere between 1 to 10 wavelengths, you can solve your model with solvers like method of moments or finite element methods. Now, if the problem size increases, and let's say your electrical size is now somewhere between 10 wavelengths to maybe around 150 wavelengths. In those kind of cases, you can then switch on to another solver like MLFMM, and you can also use maybe physical optics towards the higher side of the electrical size, higher frequencies. And let's say if your model is even larger, from around 150 wavelengths onwards, you can then move on to high approximation methods like RLGO and UTD. Now, when you're also solving these methods, one thing to keep in mind is that the mesh is different for each solver. Um, so for example, with the classical method of moments, you might have a more denser mesh. But let's say if you move on to a more high frequency method, like over here on the top, we have large element physical optics. Just by looking at the image, you can compare and see that the mesh element size is quite big when it comes to the asymptotic solvers like physical optics and RLGO. So based on the electrical size of your problem, you can keep on switching between the methods. So here is an example of an antenna placement on a large structure, which was solved with different solver techniques in Feko. So when you're solving your problem at around 2 megahertz, which is around zero point 0.8 wavelengths in size, it takes only about 14 seconds and 225 megabytes to solve it with method of moments. But the same problem, if you increase the frequency and maybe make it to 5 gigahertz, for these kind of cases where your problem size is now 2000 lambdas or 2000 wavelengths, you can switch your solver method from method of moments to maybe a combined of method of moments and physical optics, or method of moments and UTD. And you can see that there is a huge difference between the time and the memory that it would take to solve a problem like this. So if this problem, if at 5 gigahertz, if I were to solve the same problem with method of moments, it would have taken us a lot more of memory and runtime. But since we are hybridizing the methods, or we are bringing into use the asymptotic methods, it now takes us just a couple of megabytes for solving, and just a couple of seconds over here to solve this particular problem. So if you wanted more insight on this, if you're just starting off using Feko, or if you're confused as to which solver to use for what kind of applications, you can find all of the information in the Feko user guide. We have given some examples of commonly used antennas, and here you can find which solver method is more appropriate for what kind of problems. So we have some generic or very commonly used antennas, and we also have some complex, more complex applications like biomedical applications or RCS, etc. So this table can help you in deciding what solver to choose for what kind of applications. So quickly concluding that it may not always be clear which technique to use, especially when you feel like more than one method is suitable. But generally speaking, when you're just starting off, it is recommended that you first consider the default solver in Feko, which is method of moments. And let's say if your electrical size is still large, then you can consider MLFMM. And only if these two methods don't work out, you can then explore other options. users who are looking for accuracy, they might want to first start off with a default solver and then move on to other asymptotic methods. So thank you very much for listening.